So what we were saying is that once we determine the values of k and n, we can now calculate the corresponding value of sigma flow. Okay, so we have that for the flow curve, sigma f equals to k times epsilon true to the power n. And we will apply this formula for the different points. Now, of course, for point 0 and 1, we will have different values that are far from sigma true, because in the elastic region, we have inelastic behavior. The strain hardening behavior will start after the yield point, and the strain hardening behavior will continue until just before necking. And since we said that 0.5 is after necking, then we can expect that the separation between the two curves will start after 0.4. Okay, so now if we do the graph, so after doing the calculation, here you can see the calculation of the values. So based, of course, on the formula sigma flow equals to k epsilon n, you have here the values summarized in the table. We have first, you have for the two, for 0.1, for example, you can see a difference. So for the same epsilon, sigma true and sigma flow, we have a difference between them because we are still in the elastic zone. Now, once you reached the strain hardening zone, you can see that the values are very close. So you have sigma, it's expected because we find k and n based on these points 2, 3, and 4. So as you can see, the values will be very close at 0.2, 3, and 4. Now, after 4, after necking, you will start to see a difference. So for 0.5, for example, the difference is still small because you have just passed the maximum strength, and you are close to start of necking. But at 0.6, which corresponds to fracture, you have a very high difference between sigma true and sigma flow. This is because of separation, and since the strain hardening behavior will stop when necking will start. Okay, so here you can see this effect also in the curves. So when you draw the two curves, sigma true and sigma flow, on the same graph, you can find here, for example, this is the elastic region. In the elastic region, you can see that it's not the same. The curve will be different. Now, after the yield point, you have perfect match between the flow curve and the true stress strain curve. This is expected because this is here the strain hardening zone. So we can see from here that you can see the three regions on this graph. This is the elastic region, this is the strain hardening region, and this is the necking region. Okay, so elastic, strain hardening, and necking at the end. Okay, so now you will see that when you draw the two curves, the separation point will be very clear, and you can find at which point the two curves will separate. And then once you detect the separation point, which is here, you will read the corresponding values of sigma at separation point and epsilon at separation point. And since the separation point corresponds to start of necking and correspond to the maximum load applied, then from this point you can deduce the value of tensile strength. So in case in this problem they didn't give you the value of the maximum load, you can calculate it approximately using this method. And try to find it from the curve of engineering curve. You will not be able to find it accurately because, as we have seen, it's nearly a flat plate, so I cannot identify really where the maximum is. And maybe I can know the range of the maximum, but if I want to find it accurately, I need several points, much more points in the zone to be able to trap it. On the other hand, using this method, I can trap it easily by It's correspond to the separation point. And once I find the value of sigma at separation, this is the true value. I can use now the relation between true and engineering stress. Okay, so after finding epsilon separation and sigma separation, from the first relation, since I know epsilon separation true, okay, I can get the value of epsilon separation engineering. And once I get epsilon at separation engineering, I replace in the formula of relation between sigma engineering and sigma true. So I get that sigma engineering at separation point, which corresponds to the tensile strength, is equal to sigma true at separation over 1 plus epsilon engineering, which is calculated from here. And therefore I get sigma maximum, which is the tensile strength. And here I get 0.193 gigapascal. Previously, when they gave me the maximum load, I calculated it was 0.196. So you can see that the value I obtained here is very close to the one found before. Okay, so this is why this method is very useful to determine the start of necking and the maximum strength whenever I don't have the maximum load. Okay, any question on this problem? Okay, so we will continue the correction of problems of this chapter next time. Thank you.